The analysis of variance, which is typically phrased in an abbreviated fashion as ANOVA. There are more complicated versions than the one-way ANOVA test, but that's the natural starting point, so that's what we're going to focus on. A one-way ANOVA is useful if you have quantitative data, you want to compare means, and you have more than two of them. The hypotheses are there written symbolically and in words. In both cases, the null hypothesis is that all population means are equal. The alternative is that it's not the case that they're all equal. They don't have to be all different, but there has to be a difference somewhere. The conditions for inference. First, this only makes sense for quantitative data. You want to have samples that are independent of each other, and as usual, the easiest way to accomplish that would be to take random samples. The third bullet point is actually a really big deal for an ANOVA test, the assumption that all the population variances are equal. The way that you check it is to construct side-by-side box plots, and as long as the boxes are of similar size, that's considered to be good enough. The thing that would be problematic is if you had one box that was a lot bigger than another box when you're looking at those box plots. The last thing, the distribution of the residuals or errors needs to be approximately normal. You can apply the central limit theorem if your sample sizes are big enough, but if not, then you'd want to look at either a histogram of the residuals or a normal probability plot. If the null hypothesis is that all the population means are equal, looking at these two pictures, it looks like you'd reject the null in the picture on the right, but you wouldn't reject the null in the picture on the left. That's accurate. That intuition is correct. But the sample means are identical in both pictures. The thing that's different is how spread out the individual samples are. The box plots on the left are much more spread out than the box plots on the right. So that means that the variation within the groups on the left is a lot bigger. The thing that may not make sense right away is that even though this is a test involving means, it's called the analysis of variance. This is a big reason for that nomenclature. The way that you compute the test statistic is as a ratio of two variances. You have the variance between the different groups and the variance within the groups. So if you can take all of the variability, break it up into those two variances, and then you take that ratio, that's your test statistic. In those pictures, the variance between groups is the same because the sample means are identical in both pictures. But the variance within groups is going to be a whole lot different. It's going to be much larger in the picture on the left than the picture on the right. So that means that the picture on the left would have a smaller test statistic, the picture on the right would have a larger test statistic, because that variance is the one that goes in the denominator. So where the test statistic formula is written out, where it's written as MST divided by MSE, or mean square due to treatments divided by mean square due to error, those mean squares are actually variances. That isn't always the nomenclature that's used. Some books say treatment and error, some books say between and within, but really you end up with the same thing. It's the variance between samples divided by the variance within samples. The other thing that I wanted to point out here is the F as the test statistic notation. I always just write the test statistic as TS, but if you want to do it based on what distribution you're using, the correct one would be F, because we have to use an F distribution to compute the p-value when we eventually get there. We'll go through the computations of the numerator and denominator of the test statistic individually. First, the numerator, the mean square due to treatments. How do you get that? For what we're going to do, the important part is at the bottom, that the mean square due to treatments can be computed as the sum of squares due to treatments divided by k minus 1. That's the part that you're actually going to have to do. But to back up a little bit just to see where this actually comes from, if k is the number of groups or populations being compared, you have n sub I and x bar sub I for each sample, and then x double bar is the pooled sample mean, where if you just combined all the samples together and took the sample mean of that giant group, that's your x double bar. The way that you compute the sum of squares due to treatments would be using that formula. It's a weighted sum where the sample sizes are the weights of the squared distance between the sample mean and the pooled sample mean. The reason I wanted to point this out is that the variance in the numerator is ultimately based on the spread of the sample means. However, when you compute the variance in the denominator, that one revolves around the sample variances, which would be a measure of the spread within the groups. So again, the important part is at the very bottom. The way that you can compute the mean square due to error is to take the sum of squares due to error and divide by capital N minus K, where capital N is what you get when you add all of the individual sample sizes together. If you want to view that as being the pooled sample size, that would be the correct terminology. But again, I think it's worth it to run through where this actually comes from. So if you have all of the sample variances, you can compute the sum of squares due to error based on that. So this really is based on the variances within the individual samples. To compute the p-value of a one-way ANOVA test, you do use an f-distribution. Like a chi-squared distribution, the f-distribution is right-skewed. Unlike a chi-squared distribution, there are two values for the degrees of freedom. The way that we set up the test statistic was as a quotient where we had one variance divided by the other variance. Those both have degrees of freedom that go with them. So there's a value for the degrees of freedom that goes along with the numerator, and there's a separate value for the degrees of freedom that goes along with the denominator. You can see them down toward the bottom of the screen, that for a one-way ANOVA test, the numerator degrees of freedom is k minus 1, and the denominator degrees of freedom is n minus k. So when you go from sum of squares to mean square, the thing that you're dividing by is your degrees of freedom. And then lastly, just like with a chi-squared test, it's always going to be a right tail when you're computing the p-value. This is the conventional way of displaying all the computations that we'd have for a one-way ANOVA test. If you look at what you'd have to do here, a lot of it really ends up being division. If you already have the sum of squares and degrees of freedom figured out, then there's just a lot of division. Because in order to get the mean square, it's generally the sum of squares divided by the degrees of freedom. Then in order to get the test statistic, which is the thing labeled F ratio, that's also division since that's the ratio of the two mean squares. So a decent amount of putting this table together really ends up being just dividing stuff. We'll go through an example. The one that's in the third extra credit assignment is very similar to this. First of all, suppose we want to compare the mean weight loss after 1 year for 4 diets. That means we're going to be comparing 4 population means. So we can see that in the hypotheses, where the null is that mu1 equals mu2 equals mu3 equals mu4. All 4 population means are identical, or the mean weight loss is the same for all 4 diets, to be a little more specific. Then the alternative, it doesn't have to be that they're all different, but just that there's a difference somewhere. So the mean weight loss is not the same for all 4 diets. In other words, there are at least 2 diets where the mean weight loss is different. What we know so far is that there are 4 diets, so k is going to be equal to 4. And it also says in the second sentence that there are 160 subjects in the study, so that's capital N, since that's the total number of subjects taking part. Then the sum of squares due to treatments and the sum of squares due to error were given, so we know what those are. And then we can get the degrees of freedom. If k is 4, the degrees of freedom for the numerator is k minus 1, so that's going to be 3. And then capital N is 160, so the degrees of freedom for the denominator, capital N minus k, would end up being 156. This is what we have so far. We'd figured out the degrees of freedom, the sum of squares were given, and to get the values in that total row, the easiest thing to do is probably just to add down the columns. Although you could also get the 159 as capital N minus 1. The next 3 items in the table are quotients, so we just have to divide in order to get them. Generally, the mean square is equal to the sum of squares divided by the degrees of freedom. We can do that for the treatment row and the error row. We get 119.94 for the mean square due to treatments, 34.08 for the mean square due to error. And then once we have the 2 mean squares, the test statistic, or F ratio, will be the mean square due to treatments divided by the mean square due to error, and we end up with 3.519 rounded to 3 places. Here's an updated version of the ANOVA table with the mean squares and test statistic in there. Now all we have left is the p-value. So to compute the p-value, we need to use an f-distribution, more specifically one with 3 degrees of freedom in the numerator and 156 degrees of freedom in the denominator. StatKey will prompt you for those. After you put those in, it'll be a right tail test, so make sure you select that in the upper left, and then the cutoff should be the test statistic, which is 3.519. We end up with a p-value of 0.017. There's a completed ANOVA table, and now we can put the conclusion together. The p-value is less than alpha, so the null hypothesis should be rejected, and that means there's sufficient evidence to conclude what's in the alternative. Here, that would be that the mean weight loss is not the same for all 4 diets. Lastly, I just wanted to go through in real time how you would get the p-value using StatKey. Under theoretical distributions, you want the f-distribution. Then we'll get prompted for the degrees of freedom. We wanted 3 numerator degrees of freedom and 156 in that example with the diets. Then we want a right tail bounded by 3.519, and there's the p-value, 0.017.